2D element করি, we started with the CST element, which was a triangle element, three-noded triangle element. Okay, and in natural coordinate, that was represented with a right angled triangle. Okay, but that need not be a right angled triangle. যদিও বাঁদিকেরটাও right angled triangle automatically হয়ে গেল, but in general that is an arbitrarily shaped triangle. So we learned about CST element, and what we found out that that the stiffness matrix, element stiffness matrix, and other matrices and other vectors, uh, that uh, that is defined like this. That is a general representation for the stiffness matrix: B transpose D bar B. All of these are different matrices times D omega. What is omega? Omega is basically differential volume. Okay, so this thing is omega in the interior, and the boundary is called gamma. And of course, you know that gamma is the union of two subsets, the gamma t and gamma u. Gamma u is where we apply boundary condition, and gamma t is anything that is not gamma u. And the intersection of gamma t and gamma u is a null set. Okay, it means I cannot constrain the object over here and also be applying forces in the same direction. Now this is a general expression for the stiffness matrix, and what we saw in case of CST element, or the constant stress or the constant stress triangle. And if you move to 3D, that would be the constant stress tetrahedron or the constant strain tetrahedron. That means within the element, the stress or the strain is constant. So the quantities like stress and strain are constant. Each component is a constant, and basically each term in the B matrix are constants. Okay, now this we reduce to this quantity to be determinant of J times the thickness H times d xi d eta. That's how we represented the integration. And depending on what sort of element are we working with, the limits on the of the integration would change. For example, for CST element, since the inner integration is with respect to xi, that would change between 0 to 1 minus eta, and the limits on eta would be from 0 to 1. Whereas if we are dealing with a four-noded quad element, okay, so this is an arbitrary four-noded quad element in natural coordinate system. This would look like a square of side length 2. So this goes from -1 to 1 then 1 and -1. Okay, so these are the four nodes of the four-noded quad element. Okay, so for a four-noded quad element, those limits should be from -1 to 1, and the order of integration doesn't really matter. But the problem here is that if the B matrix is not a constant, these are functions of xi and eta. So B is linear in xi and eta, which means actually, to be frank, it is not also linear. Okay, if you look carefully on the video in which we discussed about four-noded quad element, this is only linear when J is a constant. The Jacobian matrix is a constant, and when is J a constant? That implies the physical element is a parallelogram. So So this has been discussed in the lecture in which we discussed four-noded quad element. Okay. So if the physical shape of the element is that of a parallelogram, okay, which means, the parallelogram is the global set. It means the rhombus, the square, the rectangle all fall under the category of parallelogram, and the general parallelogram as well. For those cases, okay, it can be shown that the Jacobian matrix is a constant, and then only the B matrix is linear in xi and eta. Okay. Now, obviously, this product would be quadratic in xi and eta because B comes twice. Okay. But then the integration becomes very difficult. Okay. Because first of all, you'll have to multiply each term. Okay. So if you want to integrate this thing symbolically, okay, such problem was not there in CST element, because in case of CST element, the B matrix, the T matrix, and everything was constant, which means you could simply write KE for CST element is the area of the triangle, okay, times B transpose dB, because that value is same everywhere within the element, okay, because it is constant, okay, and times the thickness of the triangle, which would represent the volume of the triangular element. So you need the area of the triangle, let's say A, and the thickness H, then B transpose dB. Each term was constant. When you move to four-noded quad element, the B terms are linear. The B terms are linear in xi and eta, even when the physical element is a parallelogram. Okay, so if it is a square or a rectangle or a rhombus or any general parallelogram, these are linear in xi and eta, and that's when you are lucky. But if it is a general mm, quadrilateral, this J is also not constant. Okay, you might remember that the terms within the B matrix come from del n del xi matrix. Okay, where you take the gradient of the shape functions with respect to xi and eta times the J inverse. Okay, so terms from this matrix come to B matrix. So this matrix is actually del n del x matrix, where you take the derivative of the shape functions with respect to the physical coordinates. So uh, so you are multiplying with J inverse. J being a matrix, you are multiplying with its inverse. Now imagine J is also not a constant. J is also functions of xi and eta. Okay, let's say J is also functions of linear in xi and eta. Or so what will happen is that it's a very complicated form. This B matrix, the terms in the B matrix will be in general very complicated terms. So there would be terms. I mean, if you take a single term of B matrix, let's say Bij, and let's say that has a term in the numerator and the term in the denominator, both could be functions of xi and eta. Both would be functions of xi and eta. And in a situation like this, to perform the exact integration could be really difficult. Okay, এই অবধি বোঝা গেল কি?
Yes, sir.
আচ্ছা, such problem was not there with the CST element. এবার so when we are trying to perform such integration, okay, let's say I want to evaluate the stiffness matrix, so we need to go for something called numerical integration. So that I am planning on discussing today. Okay, so keep this term in mind. But then before that, let's see, so essentially if we are planning on getting the exact integration, okay, then we are limited to only CST elements. Okay, we could not even consider the linear, bilinear rather. So it is linear in xi, linear in eta. Okay, hence bilinear. Bilinear quadrilateral element. We cannot even consider the bilinear quadrilateral element if we are strictly into direct integration. Now that's why we need numerical integration, and when we employ numerical integration, we can go even further than this. We can consider higher order elements. Okay, so I'll discuss the higher order elements first, and then we'll go for numerical integration. So higher order element, for that we need Pascal's triangle. Okay, and this kind of looks like this. You can think of 1 equals xi to the power 0 eta to the power 0. Xi equals xi to the power 1 eta to the power 0. Eta equals xi to the power 0 eta to the power 1. Okay, so these are the terms that participate in making the shape functions. Okay, so if you notice the first three terms, they make the shape functions of the CST element. If you recall, for a CST element, the shape functions are xi, eta, and the third shape function is 1 minus xi minus eta. Okay, so these are the terms that are required to construct those shape functions. When you move to four-noded quad element, you need these four terms. So this one is for CST, this one is for four-noded quadrilateral element. Okay, so for example, in case of four-noded quad element, if you take the ith shape function, let's say the first shape function, and that would be 1 minus xi by 2 times 1 minus eta by 2. Okay, so essentially you get terms like 1 minus xi minus eta plus xi eta divided by 4. Okay, so these four terms you will get. So these are coming from over here. So that's how you construct the four-noded quad element. Now let's move on to higher order terms. Okay, now if I want to construct a higher order triangular element, okay, so I should be taking these three vertices, and then I should be considering mid side nodes. Okay, so then I can mark them as 4, 5, and 6. Okay, so then I'll be requiring terms up to this line. Okay, so this is for 6-noded triangular element. Okay, but we'll not go into the details of 6-noded triangle element. Actually we can. So for example, if we construct the ideal triangle, okay, so this is the ideal triangle, and then we will be taking nodes in the middle. Okay, so let's say this is node number 4, whose coordinates are 0.5, 0. Node number 5, whose coordinates are 0.5, 0.5, and node number 6, whose coordinates are 0, 0.5. Okay, so so I will show you how to construct the different shape functions. For example, we have learned two things from the shape functions. One is the ith shape function at the ith node would be equals 1, and and um, and the thing is, at any other node, sorry, One second. At the ith node, the ith shape function should be 1. So if I equals j, it is 1. And if it is not the case, then it would be 0. Okay. So that is the criteria for choosing shape functions. Okay. So for example, if we are talking about n3, okay, n3 should be 0 on all the other 5 nodes, which means n3 should be 0 on the line 4, 6 and on the line 1, 2. Now, can you tell me what is the equation of the line 1, 2?
Y equal to X.
No. Equation of the line
Oh,
1,
sorry,
2
Y
is
equal to
xi
X.
X plus
plus
y
eta
equals to
equals
1.
xi plus eta equals
Oh,
1.
that plus it
Equation
equals
of
1,
the,
yes.
and for
Oh,
this second line, what is the equation?
Half.
Xi plus eta equals 0.5. Okay, so on these two nodes, on these two, xi plus eta equals 0.5. Is this how it is supposed to be? Is this how it is supposed to be? Yeah, yes, that's how it is going to be. So n3 is 1 minus xi minus eta times 0.5 minus xi minus eta. Okay. Now, if I write it like this, I'm surely getting a value of 0 at all the other 5 nodes except for 3. Okay. So at 3, the value would be something, but other than the node number 3, everywhere else, this shape function is going to be 0. Now I need to normalize n3 such that when I evaluate n3 at 0, 0, okay, here the value that I'm getting is 0.5. So what I need to do is I need to multiply this whole thing with 2. So essentially I should be writing it like this. So this is the way to find out the any given shape function. Okay, so this is the expression for the shape function. Okay, for the I mean the n3, the third shape function. Now there will be 6 such shape function, and you can use you know different ways to evaluate that. Okay, for example, if you are trying to figure out n6, you need something that is 0 on this line and also on this line. Now equation of this line is eta equals 0. Okay, and equation of this line is xi plus eta minus 1 equals 0. Okay, so here if you substitute uh, 0.5 and 0, so you need to multiply with minus 4. So if you take it to be like this, 1 minus xi minus eta, okay, so essentially it would satisfy both the conditions.
স্যার এই জায়গাটা আরেকবার
Okay,
বলবেন এর জায়গাটা
হ্যাঁ কি করলাম আমি দেখো, so n6 should be 0 on this line, right? আমাকে দুটো লাইন বার করতে হবে যে দুটোর মধ্যে 0 হবে. So n6 should be 0 on this line, this line 0 1, I mean sorry 3 1. এটা বোঝা যাচ্ছে?
1 2 আর 3 1 এ 0
হ্যাঁ 1 2 আর 3 1 এ 0 হবে. Now what I'm writing is the equation of line 1 2 and equation of line 1 3. Okay, now that way n6 would be 0 on both of these lines, but it would be non-zero at the node 6 itself. Now at node 6, I'll not be automatically getting a value of 1, but I need to get a value of 1. Whatever value I get, let's say I'll get 0.25. Okay, if I do not put this 4, if I do not put this 4, I'll get zero point 0.5 because eta is 0.5 and xi is 0. Okay, so I'll get 0.25. So automatically I need to divide this whole thing with 0.25. I am normalizing this with the value so that I get a value of 1. Okay, when I come to node 6. But since at every other node the value was already 0, whatever number you normalize that with, it will still be 0. বোঝা গেল? এই পার্টটা বোঝা গেল?
হ্যাঁ স্যার।
Okay. Okay. So you can construct the remaining part, and that way you can follow the same procedure. Okay, and the rest of the procedure is very same. That one good thing about finite element method is once you learn how to do the formulation for one type of element, you can do that for any other type of element. So I'll leave it over there. Okay, and I'll move to quadrilateral elements. Okay, now how do I make quadratic quadrilateral elements? Now quadrilateral elements, okay, when we had the linear element, that would be linear in both xi and eta. Okay, when I'm directly drawing the quadrilateral in the natural coordinate. I'm no longer drawing in the physical coordinate. Okay, so this one is -1 and 1, this one is 1 and -1, this one is 1 and 1, and this one is -1 and 1. Okay, so the ith shape function look like this: 1 plus xi I xi by 2 times 1 plus eta I eta by 2. Now individually these are the shape functions for the bar element. Okay, linear bar element. Okay, and essentially it's like a bar element in xi direction is multiplying a bar element in eta direction. Okay, that's what the shape functions are for a linear 4-noded quad element. That is actually bilinear. Now when you move to quadratic element, that also becomes biquadratic. Okay, so the 4-noded is bilinear. From bilinear we move to biquadratic. Okay, and for that I need this set of terms in my shape function, and there are total 9 such terms: 1 2 3 4 5 6 7 8 9 7 8 9. Okay, 5 6 7 8 9. So how will the nodes appear? So this is the 5th node, this is the 6th node, this is the 7th node, this is the 8th node, and this is the 9th node. Okay, so again the shape function, okay, would be for example n1 would be like this: xi times 1 minus xi divided by 2 times eta times 1 minus eta divided by 2. So basically I need to be multiplying the shape functions of quadratic bar element. Okay, individually these are the shape functions of quadratic bar element. Okay, and if you also like to use the previous approach, then you need to think that the shape function 1 should be 0 on this line and this line. Okay, that means xi equals 0 and xi equals 1, and also it should be 0 on eta equals 0. Okay, so this is 0 0 and eta equals 1. Okay, now you can do that, or you can directly use the shape functions for quadratic bar element because we have already done that, okay, to identify the different shape functions of the 9-noded quadrilateral element. Okay, now this 9-noded quadrilateral element is the theoretically consistent quadratic element. I would explain what is not theoretically quadratic and what is quadratic. But for the time being, can you appreciate that we can identify the shape functions of 9-noded quadrilateral element either from quadratic bar element or by using the method that we used for 6-noded triangle element. এই অবধি বোঝা যাচ্ছে তো কিভাবে শেপ ফাংশন গুলো পেতে হবে?
হ্যাঁ স্যার, মানে যে লাইনগুলোতে আর কি ওটা জিরো হচ্ছে সেই লাইনে
জিরো হবে, হ্যাঁ, সেখান সেই তার ইকুয়েশন গুলোকে মাল্টিপ্লাই করতে হবে, and then you substitute the coordinate of the respective node, okay, and then you'll get some value. You just normalize the whole expression with that value. Okay, আচ্ছা, এবার একটা জিনিস দেখাতে চাই, that there is something called a serendipity element. Okay, so this and the serendipity element looks like this. So these are xi eta coordinates and this is 0 0. Okay, and these are 4 nodes, then there is 5 6 7 and 8, but not the 9th node. So it is 8-noded quadrilateral element. Okay, so these are the terms for 9-noded quadrilateral element. Okay, for 8-noded quadrilateral element, what we would do is we need to get rid of one of the terms because the number of nodes is same as the number of shape functions, and that is also same as the number of terms in the shape function. The general set of terms, okay, in the polynomial should be exactly the same. Now, which of the terms do you think should we omit? কোন টার্মটা মনে হচ্ছে তোমাদের এদের মধ্যে অমিট করা উচিত?
স্যার জাই স্কয়ার ইটা স্কয়ার।
কেন?
স্যার ওই টার্মটা তো মানে এইখানে তো মানে যেহেতু মানে মিডিল এলিমেন্টটা নিচ্ছি মানে নেই নাম্বার 9টা, তো ওখানে জাই ইকুয়ালস টু 0 আর ইটা ইকুয়ালস টু 0 ওই দুটো লাইন কনসিডার করা হবে না।
So that means I can also remove xi eta, right? Or for that matter xi or eta. আচ্ছা, আমি একটা জিনিস বলি, the first of all there are certain rules for choosing shape functions. The shape functions should be complete from the lower order to higher order. Okay, so that way you only get to skip the highest order. Okay, and also since the element, okay, should not be partial to either in xi or eta direction, you cannot skip a non-symmetric term. Okay, you should always keep a term that is symmetric in xi and eta, hence xi square eta square, and it is also the fourth the highest order term. Up to xi square eta square, only these are only cubic terms. Okay, so this is a constant linear term, quadratic term, cubic term. That is where it becomes fourth order term. Shape function should be complete from lowest order to highest order. Okay, I mean, you see, when we are working with linear quadrilateral element, this many terms we didn't skip any of the terms. Okay, when we move to higher order terms, okay, and then we didn't have any of the higher order terms in 4-noded quad element. But when we moved to 9-noded quad element, we took all the 9 terms and we also included terms from the 4-noded quad element. Okay, it is very inclusive. Okay, so when we are dropping one term, okay, from the set of from the polynomial, that has to be the highest order, and that also has to be symmetric in xi and eta. So the only term that qualifies for that is xi squared eta squared. Okay, so that is the term we would like to get rid of. So when we get rid of this, okay, what you would be getting up to this is the 8-noded quad element. Okay, now imagine what would be the shape functions for 8-noded quad element, and I'll explain to you why do we need a serendipity element, or why do we need a 8-noded quad element. Okay, now this time it would be tricky. Which of the direction should you take? First of all, notice that you are getting constant terms, linear terms, quadratic terms, and up to cubic terms. That means in your shape function you can use 3 linear equations. Okay, for example, if I have to find out the shape function for node 1, I'd be considering this line, the line 4 3, whose equation is eta equals 1. That means 1 minus eta. Okay, 1 minus eta equals 0. So I'll be considering this line, so that on this line shape function 1 is 0. Now this line on xi equals 1, it is also 0. Okay, but then I'll be not considering either 8 6 line or 7 5 line. I'll simply be joining 8 and 5, because I only have the freedom to incorporate 3 linear equations. Okay, because I am going up to cubic term. Okay, এই পার্টটা বোঝা যাচ্ছে তো? আমি up to cubic term যাচ্ছি, so I have the freedom to go up to 3 equations. এই জায়গাটা বোঝা যাচ্ছে?
হ্যাঁ স্যার।
Okay, so now you need to write the equation of line 5 8. Okay,
ওটা xi plus eta plus 1 হবে, মানে xi plus eta equals to -1.
xi plus eta equals -1. So 1 minus 1 plus xi plus eta, that is the equation. 1 plus xi plus eta. So when xi is 0, eta equals -1. When eta is 0, xi equals -1. Okay. Now you have the 3 terms. Now you need to substitute for this thing evaluated at -1 and -1. So this is going to be 2 times 2 times -1. Okay, so you need to divide this thing by -4. Okay, so that is the shape function 1, and this way you can continue to write the expression for the shape function.
স্যার এইখানে আমরা মানে 5 8 এর মতন যে মানে লাইনটা নিলাম, তুমি 6 7 এর জন্য কেন নিলাম না?
6 7 এর জন্য কেন নিলাম না?
কারণ কি স্যার ওইগুলো ওই 2 3 আর 3 4 এ কভার করে নিয়েছে ওই কারণে?
হ্যাঁ, না, কারণ হচ্ছে যে তোমার কিছু কনস্ট্রেন্ট আছে। Since you can go only up to cubic term, so that means the maximum number of lines that you can take is limited to 3.
Okay sir.
Okay, and yes, it should not also, it cannot also be the line containing, you see, the shape function must be 0 at 5 as well as at 2, but it is non-zero at 1, hence you cannot take this line. Similarly, you cannot take this line. Okay,
yes sir,
but by taking this line 4 7 3, you can set it 0. Okay,
yes sir,
on each of these nodes. Similarly for 3 6 2. Okay, then you only have to take care of only 2 nodes, and you can of course construct a line through 2 points. Okay, so that way it is the the simplest way to arrive at a shape function.
Okay sir.
If you consider this line and this line, and after that you also consider 7 6, that is a redundant exercise, and by that it becomes a 4th order polynomial, and you start getting terms from over here and over here. সেটা একটু প্রবলেমেটিক হয়ে যাবে। আচ্ছা, so clearly বলছি, আজকের তোমাদের অ্যাসাইনমেন্ট হচ্ছে টু ফাইন্ড আউট দ্য শেপ ফাংশনস, all shape functions for the following elements 60, 9q, 8q. Okay. আচ্ছা, এবার I need to discuss one more thing about the serendipity element. মানে আমরা কেন quad মানে you see we are talking about quadratic quadrilateral element in which we have seen both 9-noded and 8-noded quadrilateral element. Okay, why am I calling this to be quadratic? You see, individually xi squared and eta squared terms are still obtained in 8-noded quad element. Okay, that's why it is quadratic in xi as well as it is quadratic in eta, but you get to drop one node. Okay, you get to drop one term from the shape function, and that is not the only advantage. There are few more advantages. So ধরা যাক I have a huge object and I have a large mesh. Okay, and initially let's say I'm modeling with 4-noded quad element. Okay, so there are 4 nodes. Okay, and you see I'm only showing a part of the mesh. The actual geometry is much bigger and the mesh is also very big. Okay, or for that matter I can take the location of the element at a different region. So 1 2 3 4. Okay, for a 4-noded quad element, okay, let's say each node, let's talk about the node number 1. Okay, how many elements does this node is how many element share this node? মানে 4 nodes, 4 elements. Okay, and same goes for all the 4 nodes. So effectively the ratio n node to n element is 4 times 1 by 4. So each node is shared between 4 elements. Okay, so the element so the share of this element on node number 1 is 1/4, and same goes for each of the 4 nodes. So node count to element count, okay, in a very large mesh, okay, very large mesh, it is approximately 1. Okay, বোঝা গেল? Is this clear? If I have a very large mesh, the number of nodes and number of elements would essentially be very close to one another. Okay, obviously the number of nodes would be higher, but it would be very close to the number of elements. এই অবধি বোঝা গেল? আচ্ছা, এবার দেখো যদি if I shouldn't be showing 4-noded and 9-noded element in the same mesh, but I'm doing that. Let's say I have 9-noded quad element. Okay, so there would be 1 2 3 4 nodes which are shared among 4 elements. Then there would be 4 more nodes, 5 6 7 and 8. Each node is shared between 2 elements. এটা দেখা যাচ্ছে, node number 6 is shared between only 2 elements. Okay, and the 9th node is not shared with anyone. Okay, So the mesh count, I mean the number of elements to number of nodes is 1 because the ninth node is not shared, plus 4 times half plus 4 times 1 by 4. Okay. So total mesh count becomes 1 plus 2 plus 1, 4. Okay. Okay. In a similar way, if I take 8 noded quad element, okay, for a large mesh, number of nodes to number of element ratio, that would be 4 times half plus 4 times 1/4, a total of 3. Okay, so it's not dropping off only one node. It is actually 25% saving in number of nodes and number of degrees of freedom being for each node the displacement in two direction, ux and uy. So each node has 2 degrees of freedom. So it is 25% saving on number of nodes and number of degrees of freedom, and therefore it's a lot of saving in computational time. Okay, when you move to 3D, that is,
Sir,
you
a
move to,
number of degrees of
হ্যাঁ,
freedom equals to twice into n node এটা 9q এর জন্য।
সবার জন্য,
আচ্ছা।
মানে 4 নোডেড কোয়াড্রিলেটারাল এলিমেন্টের জন্য যা, মানে you see each node has 2 degrees of freedom. It can move in x and move in y. Okay, এবার নাম্বার অফ ডিগ্রিজ অফ ফ্রিডম এর উপর ডিপেন্ড করে যে তোমার ক্যালকুলেশন টাইম কত হবে, স্টিফনেস ম্যাট্রিক্সের সাইজ কত হবে। The size of the stiffness matrix is NDF by NDF. Okay, the global set, the global number of degrees of freedom. So when you reduce the number of nodes, you actually reduce the number of degrees of freedom by the same percentage. Okay, and when you go for brick element, you know that the linear brick element has 8 nodes for linear. Okay, similarly, if you take quadratic shape function, that would be 27 nodes. Okay, now out of these 8 nodes, each of these should be shared with all the elements, I mean 8 elements. Okay, so for 8 noded brick element, okay, you can imagine this type of a mesh in 3D. So each of the nodes would be shared with 8 elements for the 8 noded brick element. So n node to n lm is approximately going to be 1, just like the 2D case. However, for quadratic element, there would be mid side nodes, mid face node, and mid body node. Okay, so there would be 8 mids, so n node to n element ratio. Okay, so the mid side node, so first of all the vertices or the n nodes, okay, that will contribute to 1 because that will be shared with 8 elements. Each of them would be shared with 8 elements. Now these mid side nodes, and you see there are 1 2 3 4 5 6 7 8 9 10 11 12 sides, and each side will have one mid side node. Okay, and each side would be shared with 4 elements. So 12 times 1/4. Okay, then there would be mid face nodes. Now there are total 6 faces. Okay, so 6 times, and each face would be shared with 2 elements. Okay, so 6 times half plus one mid body node, that is one additional node. Okay, hence the number of nodes to number of element ratio for a large mesh is going to be total of 8. Okay, but what we do is we take serendipity element in 3D, and in serendipity element so there would be corner nodes, then there would be mid side nodes, then there would be mid face nodes, and there would be mid body nodes. Okay, this many nodes are required for a theoretically consistent element. Okay, but if you want to use serendipity element, you get to skip these two. So these are only taking part in serendipity element. If you do that, then what you get is you only be working with 4 nodes in 3D: the mid side nodes and the corner nodes, which is exactly half compared to the theoretically consistent one, which means you get to save 50% in your total, number of degrees of freedom. Okay, when you are using serendipity element, the term serendipity means that you getting something for a lower price. Okay, or you getting something what you didn't expect. Okay, so the thing is, by using a lesser computational volume, okay, you are employing quadratic behavior in the element. Okay, and what are the advantages of quadratic behavior? That has been discussed in the early classes of this course. Okay, so you get to employ quadratic behavior but with lesser computational volume. Okay, so that's where the name comes from. But then the serendipity element has its own issues. Okay, uh, because there is no free lunch. Okay, so serendipity element comes with its own set of issues, and the issues are typically observed in when you are doing electrostatic analysis, say, or thermal conduction analysis. You start getting problems like overshoot and undershoot if you employ, serendipity elements. Okay, what is meant by overshoot and undershoot? Imagine you have a block. On the left side you have applied a temperature of 0 degrees Celsius, and on this side you have applied 100 degrees Celsius of temperature. So temperature everywhere in between should be between 0 and 100 degrees Celsius. Okay, overshoot and undershoot may happen. Okay, now this only happens for a very complicated problem when you have multiple layers of material and all. Okay, but this only happens if you use serendipity elements. If you use, let's say, linear brick element, okay, this doesn't happen. So you start getting temperatures below 0 degree and temperatures above 100 degree, which is non-physical. Okay, for a problem like this, imagine if you apply a voltage of 0 volt here and 100 volt here, you start getting voltages beyond 0 and 100 volt. Okay, so such problems starts to arise for a serendipity element. এই অবধি বোঝা গেল?
হ্যাঁ স্যার।
Okay. Okay. Now everything beyond CST element, okay, requires numerical integration. You cannot skip numerical integration. Okay, if you are not using CST element. So the fact is that the expression becomes so complicated, you cannot symbolically integrate and find out the expression, not in general. Okay, Now, in numerical integration, we use something called Gauss Quadrature. Okay. So the idea of Gauss Quadrature is, let's say you are trying to integrate a function of xi, okay, in the limits -1 to 1. Okay. And can that be represented like a sum of wi of f at xi I? All I'm saying is, let's say this function of yours is like this, f of xi, and xi ranges from -1 to 1. Can you take multiple locations, evaluate the function on those locations? Okay, so this one is xi1, say, this one is xi2, and this one is f at xi1, and this one is f at xi2. Okay, and then you multiply with certain weights and represent the integration exactly or approximately. Okay, so this is the idea. Okay, first we will, so first we will see the situations where we can exactly evaluate this integration. Okay, and then from that we'll identify the correct values of the weights and the correct values of the xi i's. Okay, now these xi i's are not the nodal coordinates. Okay, these are the coordinates of the something called integration points. Okay, and they are typically lying within the element.
So ওয়েটগুলো কি কনস্ট্যান্ট নাকি ওগুলো ফাংশন অফ xi?
Okay, so these inner points are the integration points. ঠিক আছে, মানে পরিষ্কার কথা, ধরা যাক the simplest Gauss quadratures, the simplest one is a one point or single point Gauss quadrature. Okay, in which you take a single xi I and a single wi. Okay, so you are trying to represent an integration. Okay, integration between -1 to 1 f of xi d xi approximately as, sorry, এখানে তো একটাই point, so one point Gauss quadrature it would be xi1 and w1. So what you are trying to do is xi w1 times f of xi1. Okay, now these are constant values. Okay, constant in terms of xi and eta, but what value of xi1 and what value of w1 should be the most effective, that we do not know at the time being. Okay, কিন্তু একটা জিনিস বোঝা যাচ্ছে যে if I take single point Gauss quadrature, there would be only two parameters that we can adjust. Two parameters, xi1 and w1. Okay, now imagine if f of xi is a polynomial. Okay, what polynomial can be accurately modeled with two parameters? What polynomial has two parameters?
Straight line.
Straight line. So if f of xi is linear in xi, let's say f of xi is c0 plus c1 xi. Okay, now here we are willing to get approximate integration. Okay, but even an approximation should be benchmarked. Okay, that means in some situations it is supposed to give you the exact value. Okay, situation like where you have a polynomial with two parameters. You are using two parameters and the polynomial also has two parameters. So a situation where it gives you exact integration of this polynomial. Okay, for that the values of xi and w, which gives you exact value of the integration when you take a straight line, okay, are the the correct values of xi I and wi. Okay, because here for single point Gauss quadrature you are only taking one point. Okay, for a single point Gauss quadrature you are you only have two parameters. Okay, so the maximum I mean uh, the highest order of polynomial that it can accurately model is a straight line. Okay, and therefore the weights and the values of the or the location of the integration point, okay, should be such that it gives you exact value for the polynomial which it can model accurately. So if I integrate this quantity between -1 and 1, first of all, please understand you are integrating between -1 and 1, and this term is a constant, and this term is an odd function. Xi is an odd function, so this term actually vanishes. Okay, whereas this term will survive, and this thing would be, so I equals twice C0, and twice C0. Okay, and what we are doing over here, we are multiplying with W1. What are we multiplying? C0 plus C1 times xi. Why are we multiplying C0 plus C1 times xi? Because f is assumed to be this function. So I'm taking the value of f at xi1. Okay, and that way we will get W1 times C0 plus C1 times xi. Now from left and right, we'll compare the coefficients of C0 and C1. I can write this thing 0 times C1, which will tell us that xi should be 0 and W1 should be 2, which means let's say if I have a linear function just like this, if this is f of xi, okay, I'll have to take its value at xi equals 0, okay, and multiply it with 2, which is the distance between -1 and 1, and this area is same as this area also, because this triangle that you have skipped in the first part has the same area that this additional triangle that you have considered in the second part. Okay, so that way you get the exact solution. Now a straight line might also have C1 equals
বলছি এখানে যখন W1 into f of xi করলাম তাহলে এটা W1 C1 xi হবে না, মানে W1 C0 plus W1 C1 xi।
হ্যাঁ 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 W1 C1 xi, I stand corrected. So but that also will give you C1 equals 0, sorry, xi equals 0. আচ্ছা, তা এতে আমরা কি বুঝলাম যে if we are integrating a constant or a linear function, I mean even if f of xi equals C0, okay, we can use a single point Gauss quadrature. For example, if we are integrating B transpose dB, and that for a CST element is a constant, then actually this times determinant of J, okay, that we are integrating with respect to xi and eta. Since this term is a you see this term is a constant, okay, for a CST element we can use a single point Gauss quadrature, okay, and that location of the single point Gauss quadrature should be xi equal 0.5 and eta equals 0.5. Why 0.5? Because for a CST element xi ranges from 0 to 1 and not -1 to 1, so you need to adjust the scale accordingly. So for a, and because it is a constant, actually for CST element you don't have to do the numerical integration at all, but for the proof of concept we can say that if we need a single point Gauss quadrature, that should be at xi equal 0.5 and it equal 0.5. Actually because this term is constant, it will be constant everywhere. Now let's move on to four noded quad element. Okay, if we now what we have learned that for single point Gauss quadrature the weight should be 2 and the location of the coordinate should be 0. Achha. Let's move on to four noded quad element. Okay, I'm not going for higher order element, let's just stick to four noded quad element. Even if the four noded quad element were to be a parabola, then also B transpose dB would be quadratic functions. Each term in this product should be quadratic in xi and eta, even if determinant is J is a constant. Okay, and if it is not, then that is altogether a different situation. But even if we consider a simplest situation where J is a constant, the Jacobian is a constant, this is still quadratic in xi and eta. Okay, now in that situation, that means when the physical quadrilateral is indeed a parallelogram, if it is not, then it is a different situation. But if it is even a parallelogram, then how many Gauss points do we need? Okay, first of all, since it is parabolic in xi and eta, let's say if I take a parabolic function, a cubic function, a cubic function or a quadratic function. Okay, so this would look like this: C0 plus C1 xi plus C2 xi squared. Obviously, this cannot be exactly integrated. The integration cannot be exactly evaluated, okay, using a single point Gauss quadrature. But if we move for 2-point Gauss quadrature, so we'll have two pairs, W1 xi1 and W2 xi2. Therefore, we'll be having 4 terms. Okay, and the function, the maximum order of the polynomial function that it can accurately integrate, okay, that would be cubic. And we should be evaluating these parameters considering the maximum possibility. Okay, although for a four noded quad element which is parallelogram in physical coordinate, to exactly evaluate the stiffness matrix we need to integrate up to a quadratic term. Okay, we would be choosing the weights and the locations of the integration points such that it can exactly integrate up to a cubic function. Why so? Because we'll be incorporating 4 terms. We can only incorporate 2 terms or 4 terms. Since you will be incorporating 4 terms, therefore we need to consider the maximum order of the polynomial that it can accurately model. Okay, now if I do consider that, okay, and if I equals integration -1 to 1 f of x f of xi d xi, okay, it would be twice C0 plus no term from C1, C2 by 3, 2C2 by 3 you see xi square is a even function, hence comes the 2, but then it would be xi cube, okay, and that's why you need 1 by 3. So this is the integration, okay, and this should be equal to w1, this should be equal to c0 times w1 plus w2 plus c1 times w1 xi plus w2 xi plus c2 times w1 xi squared plus w2 xi squared, sorry, xi1 xi2 xi1 squared xi2 squared plus c3 times w1 xi1 cube w2 xi2 cube. And if we compare the coefficients of c0, c1, c2 and c3, you'd see w1 plus w2 is 2, w1 xi 1 plus w2 xi 2 is 0, w1 xi 1 squared plus w2 xi 2 squared is 2 by 3, and w1 xi 1 cube plus w2 xi 2 cube is 0. Okay, so we have these 4 equations from which we'll have to determine the values of 4 quantities w1, xi1, w2 and xi2. Now if I call these one as equation 1, 2, 3 and 4, now let's say if I multiply this one with xi1 squared, equation number 2 with xi1 squared, I'll be getting w1 xi1 cube plus w2 xi2 xi1 squared, okay, and if I subtract equation number 4 from it, so I'll get w1 xi1 cube plus w2 xi2 cube equals 0. So these two terms will cancel out. So w2 times xi2 xi1 squared minus xi2 squared equals 0. Therefore, we'll get xi1 squared equal xi2 squared. Okay. Which would say that w1 plus, from equation number 3 we'll get w1 plus w2 times xi1 squared equals 2 by 3, which would tell us that xi1 squared from equation number 1 will get xi1 squared equal 1 by 3. Okay. So eventually this would be your solution. w1 equals w2 equals 1 and xi1 equal minus xi2 equals minus 1 by root 3. Okay. So that is when you are integrating only with respect to z. But the same thing you are supposed to do while integrating with respect to eta. And in the end, if these are the nodes having coordinate plus and minus 1, okay, these are the 4 nodes, the integration points would be slightly interior. Okay, you see 1 by root 3 is around 57%. So this one is minus 1 by root 3, 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 and so on. Okay, so what you do is you evaluate this integrand b transpose db times det j. Okay, this whole thing you evaluate at this 4 integration points, and you don't have to integrate any further. You simply multiply them with the respective weights, which in this case is 1. Okay, and you simply add them up, and that is all you got to do to numerically integrate. And if you're physical, and that you do irrespective of the physical shape of the quadrilateral. Okay, if indeed the physical shape is a parallelogram, then you will get the exact value. If the physical shape is not a parallelogram, if it is a general quadrilateral, a trapezoid, let's say, then you will get an approximate solution. Okay, but that's approximation is associated with any numerical method. Okay, so this is a 2-point Gauss quadrature. Okay, and this one is known as the full integration with respect to 4-noded quad element. Okay, because you see, you could also use the single point Gauss quadrature for 4-noded quad element. No one is stopping you from using a single point Gauss quadrature for a 4-noded quad element. The process only remains the same. Okay, but the thing is, you'll never be getting exact solution. It will always be approximate. Okay, 1-point Gauss quadrature is called reduced integration. Okay, and reduced integration leads to hourglass modes. Okay, so so we'll stop here. Okay, and this is going to be your second assignment. Okay, show how reduced integration gives us hourglass modes, and also what are hourglass modes and how is that not desired. So hourglass modes are not desired in finite element solution. Okay, so you need to show how the reduced integration leads to hourglass modes, what are hourglass modes, and why are they not desirable in finite element solution. Okay, that is going to be your assignment. You'll find that in the notes. You'll also find the description of that in your textbook, and a lot of material would be available in the YouTube as well. Okay, and this is the only assignment I'm leaving. I mean, this is the only non-covered part I'm leaving for today. Okay, I might have left some of the terms that I didn't cover, some of the topics that I didn't cover. For example, beam element, truss element, and frame element I didn't cover. Okay, but I think they are simple enough for you to grasp, and same would be this one too. Okay, so
স্যার
So with
একটা
that, I have no other thing to discuss. But if you have anything to ask, please go on.
হ্যাঁ স্যার একটা ডাউট জিজ্ঞেস করছি
হ্যাঁ
বলছি
বলেন।
এইখানে যে আমরা এফ অফ জাই ডিজাই মানে যেটা ইন্টিগ্রেশনটা করছি এটা তো মানে আমরা প্রথমে কনস্ট্যান্টস গুলো মানে নিউমারিক্যাল ইন্টিগ্রেশন করে বার করছি মানে W1 W2 জাই1 জাই2 তো কমপ্লেক্স মানে যখন যদি কোনো ফাংশন থাকে যেটা মানে আমরা ইন্টিগ্রেট করতে পারবো না তখন কি করে করব
আচ্ছা, প্রথম কথা যেটা আমি হয়তো ক্লিয়ারলি বুঝে উঠতে পারিনি সেটা হচ্ছে যে the goal is never to get an exact solution. Okay, the goal is to get an approximate solution, but even an approximate method needs to be benchmarked so that in the situations where it is desired to give you exact solution, it should give you exact solution.
আচ্ছা
You can use a single point Gauss quadrature for a 4-noded element, and there is no way a single point Gauss quadrature can give you exact solution for a 4-noded quad element, because we have already established that B transpose dB is going to be quadratic in xi and eta, even if the physical shape is a parallelogram. That means the J matrix, the Jacobian matrix, is a constant.
Constant.
Even then, it is not going to be either constant or linear. The B transpose dB is not going to be linear in xi and eta. It is going to be quadratic.
yes
But if you do take 2-point Gauss quadrature, okay, you will get exact solution when the physical quadrilateral is a parallelogram. But if the physical quadrilateral is not a parallelogram, then you will not get an exact solution. That then it would be an approximate solution. Okay, but even the approximate methods needs to be benchmarked. Even the approximate methods needs to be calibrated, okay, or tweaked so that it should be giving you exact solution when it should. For example, if you take a single point Gauss quadrature, there you are using two parameters: one weight, one location, one coordinate. Okay, so one coordinate and one weight, these are two parameters. Now it should be in a position to give you exact solution. See, most of our functions that we use in finite element method, not most, every function that we used was polynomial in nature. So it should be in a position to integrate a polynomial, a general polynomial with two parameters. Okay, I mean, I can also represent a cubic polynomial with two parameters, right? Like C0 xi squared and C1 xi cube. I'm not talking about any particular function. I'm talking about general polynomial. Okay, a general polynomial with two parameters would be what? A straight line, a linear function. So a single point Gauss quadrature should be in a position to exactly evaluate up to linear functions. Now, up to linear function, what else is there? Either a constant value or a linear function. Okay, similarly, a 2-point Gauss quadrature. Now this time we have four parameters. You see, two weights and two coordinates. So it should be in a position to integrate up to a cubic function. Okay, exactly. You can use that 2-point Gauss quadrature, let's say, to integrate a 5th order polynomial. It would be an approximate solution. Okay, but that approximate is better than most other approximations. That's all I'm saying. Okay, I mean, there is no way you can have only two integration points, that means two weights and two coordinates, with any combination of weights and coordinates. You cannot get a better approximation than the Gauss quadrature. That's all is all my claim.
okay
You see, 2-point Gauss quadrature can exactly integrate up to a cubic function. But if you provide a 4th order polynomial, if you're trying to integrate 4th order polynomial numerically using Gauss quadrature, it will definitely give you an approximate solution. Okay, but then the claim is that you can try any other combination of the weights and the coordinates. Okay, one that is not specified by the Gauss quadrature, but you will never get a better approximation than Gauss quadrature. That's the idea.
yes
এই অবধি বোঝা গেল?
আচ্ছা বোঝা গেছে
বোঝা গেছে তো? Okay, and the similar way you can use a single point Gauss quadrature. You see, problemটা কোথায় হয়? Problemটা কিন্তু finite elemented একটাই জায়গায়. Large mesh, let's say 10,000 element, 20,000 nodes. Okay, and even more elements, more nodes, 1 million degrees of freedom. Okay, যখন ওই 1 million degree of freedom এ গিয়ে পৌঁছে যায়, তখন যেটা অসুবিধে যে it matters how much is your computational volume. Okay, মানে তোমাকে কতটা কম্পিটিশন করতে হচ্ছে। এবার 2D নয় 3D তে হবে। 3D তেও সিঙ্গেল পয়েন্ট গস কোয়াড্রেচারে কতগুলো ইন্টিগ্রেশন পয়েন্ট? একটা ইন্টিগ্রেশন পয়েন্ট। So you need to evaluate B transpose DV. You see there is matrix multiplication, which is a computationally uh, demanding job. Okay, that you need to do once. B transpose DV you need to do once for a single point Gauss quadrature in 3D. Okay, 3D তেই ভাবো, because major of the finite element method is 3D. Now majority of the finite element method. Now imagine if you want to use 2-point Gauss quadrature in 3D. Okay, let's say 8 noded brick element. Then just like the 2D case, you need 2 to the power 3, total 8 integration points. Okay, so your computational job becomes 8 times higher. 8 times higher. Okay, you see, you can use single point Gauss quadrature as a numerical integration tool, okay, for evaluating the stiffness matrix of a 8 noded brick element. Obviously it would be an approximation. Even when the physical element is a perfect cube, then also it would be an approximation. Okay, that's what we have learned from Gauss quadrature. But then if you go for the full integration, your computational cost is 8 times higher. The amount of calculation that you are supposed to do to get the stiffness matrix using full integration is 8 times higher. Okay, it's always the balance between accuracy and the computational cost. Okay, in one hand there is accuracy, okay, how accurately you can evaluate the stiffness matrix. In the other hand is the computational cost. It becomes 8 times higher. It's always that. I mean, you can, if the computational cost didn't matter, you would be refining the mesh infinitely. Then we will not be calling it finite element method. We would be calling it infinitesimally small element method. Okay, we could have been doing that. Okay, but we cannot do that because the computational cost does matter. If I do refine the mesh so much that the elements are really tiny, infinitesimally small, I'll be getting exact solution for any problem. Okay, and if I could do that, I would do that. But then the computational cost is the biggest concern. Okay, but then does that mean I can do reduced integration and be done with it? No, the reduced integration also comes with its own set of issues. There is no free lunch. If you use serendipity element in 3D, okay, your computational cost is reduced to 50%. Okay, but then also there are issues with the serendipity element. Okay, it gives you it gives you quadratic shape functions, but still it has some issues. Accuracy is the issue. So every time you want to reduce the computational cost, you need to check the other side of your scale, which is the accuracy. Okay, so if you use serendipity element or reduced integration, you need to check what sort of effect is there in the accuracy. Okay, and the major issue with reduced integration, single point Gauss quadrature, is hourglass mode. It's not even the accuracy thing. Okay, of course there is loss in accuracy, but hourglass mode is an additional problem in addition to issue in accuracy, or you can say it is one of the issues in the accuracy, but it's a major issue. You cannot use reduced integration. I mean, in finite element method, a lot of times we do use reduced integration, but with hourglass control. Okay, you need to Google this term immediately. Hourglass control. That is the one of the major things in finite element method. If you're using a large mesh, at times you would like to go with reduced integration, because even full integration has its own set of issues, not just computational cost. There are a lot of things called volumetric locking, your shear locking, all those things are there. If you're interested, you can search in the internet about volumetric locking and shear locking. Okay, so even the full integration scheme comes with, I mean, you see, people have realized all those things. We are learning a basic finite element course, but people who have been using studying finite element method for decades, I mean, the subject is not very new, so so they already have come up with this set of issues, and they also have come up with different solutions as well. So full integration method can be, there is a method called B bar method. Okay, that takes care of the issues with the full integration scheme. The issues with full integration scheme as it is, okay, I mean the theoretically correct formulation, that has issues such as volumetric locking and shear locking. Okay, I'm sorry that we didn't get a chance to discuss that. If we had more time, if the semester, I mean, if the session had begun a couple of weeks earlier, I could have discussed that, and I'd be uh, so. So those issues could be taken care of by some of the augmentations on full integration. So every finite element tool that is available commercially, ANSYS, Abacus, Nastran, whatever the case may be, they all used full integration with that sort of augmentation. Similarly, every time you want to use a reduced integration to reduce the computational cost, maybe at the cost of accuracy, but as I said, the hourglass mode is an additional issue other than computational cost. You need to use something called hourglass control. I mean, that is inbuilt in every software, but that is also there. Okay, so the vanilla version of finite element method, you cannot apply that. So this is only for you to have just a just to give you some glimpse of finite element method, but the ones that are implemented in the softwares are kind of advanced, and they kind of use these set of controls. Okay, usually I would like to talk about a little bit of those controls. I mean, there is a lot of things, okay, but I discuss a tiny fraction of that, okay, in my course as well. But then we had very limited time, so we couldn't do that. Okay, is there any other question?
না স্যার আমি কিছু
ওকে, তাহলে আর কোশ্চেন যদি না থাকে তাহলে এখানেই শেষ করছি, রেকর্ডিংও।
স্যার বলছি অ্যাসাইনমেন্টের ব্যাপারে জিজ্ঞাসা ছিল।
হ্যাঁ বলো।
স্যার বলছি অ্যাসাইনমেন্টে বিম আর ট্রাস যেগুলো বলেছেন, মানে ওটার ভ্যারিয়েশনাল স্টেটমেন্টের ফর্মুলেশন পার্টটা করতে হবে তো?
হ্যাঁ দেখো, নোটসে আছে, ঠিক আছে, নোটসে সবটাই আছে, তুমি পড়বে, বুঝবে, দরকার হলে বইয়ের সাহায্য নেবে, দরকার মনে করলে ইন্টারনেটেরও সাহায্য নেবে, ঠিক আছে, সেখান থেকে যেভাবে অ্যাসাইনমেন্টে বলা আছে সেটাকে পরপর লিখবে। ওকে,
হ্যাঁ মানে আপনি ওইটাই জাস্ট মানে 3টে টপিকই বলেছেন যে পুরোটা করতে, তো সেটাই বলছি।
ওই টপিকগুলো বলেছি, আর আজকে যেটা বললাম তোমার হচ্ছে যে আওয়ারগ্লাস কন্ট্রোল, আওয়ারগ্লাস কন্ট্রোল না, আওয়ারগ্লাস মোড কাকে বলে, এবং হাউ ইজ দ্যাট হার্মফুল অর নট হার্মফুল। I mean, in presence of hourglass mode, you cannot use finite element method. So, and then the shape functions of all the higher order elements. এই বিষয়গুলো
অঙ্ক দিয়েছিলেন আপনি। আর স্যার বলছি ফার্স্ট যে একদম কোশ্চেনটা বলেছিলেন যে র্যালিরিডস আর ওয়েটেড রেসিডুয়াল, স্যার ওটাতে কি জাস্ট মেথডটা লিখতে হবে অ্যাসাইনমেন্টে, নাকি 1D বারের জন্য ওটা কি হচ্ছে মানে ফর্মুলেশনটা করতে হবে?
না, মেথডটাকে ডিসক্রাইব করবে, কিন্তু মেথডটা ডিসক্রাইব করতে গেলে তোমার একটা অন্তত এক্সাম্পল কনসিডার করা উচিত।
সেটাই বলছি যে এক্সাম্পল হিসেবে 1D বারটাই,
এক্সাম্পল হিসেবে তুমি 1D বারের কেসটা কনসিডার করতে পারো, বা তোমার যে কোনো পছন্দের এক্সাম্পল। ইউ ক্যান ইভেন কনসিডার থার্মাল কন্ডাকশন। 1D thermal conduction equation is very similar to bar equation. Okay, so you can try that as well.
ওকে, ঠিক আছে,
ঠিক আছে, ওকে।